Hello, hello. Am I audible?
கேக்குதுண்ணா.
Hello?
Am I audible?
Yes, yes.
Sorry, are the organizers online or not?
Yes, ma'am.
Okay, so you will start in what, about 6-7 minutes?
Yes, ma'am. It will start by 10 p.m. 10 a.m. Sharp.
All right, then when you tell me, I will share my screen.
Yes, ma'am. Sure.
Thank you.
Hello, ma'am.
Thank
Yesterday
you.
I didn't give a feedback. Hello.
Yes.
Good morning, ma'am.
Yeah, morning. Okay, I'm not clear who you are speaking to.
Ma'am, I think he's trying to contact the organizers. Participants, if you have any questions, please post it in the chat box. The event will start by 10 a.m. in 5 minutes.
Okay.
Thank you.
Pleasure welcoming everyone for the second day of International Workshop on Advanced Materials and Application IWAMA2021, organized by NITT Spy Overseas Student Chapters, Department of Physics, NIT Trichy, to memorize the National Science Day. On behalf of our student chapter, I, Divya Prasad, Vice President of NITT Spy Student Chapter, heartily welcome the staff advisor, Professor D. Sasthikumar sir, the head of the Department of Physics, Professor M. Ashok sir, the technical advisor, Dr. R. Justin sir, all faculty members of Department of Physics, our invited speakers, Dr. R.T. Agrawal, Professor Ayan Banerjee, judges, students, and participants. Here we begin our today's intellectual journey with Malachi song, which is refreshing song.
கருவாக்கி உருவாக்கி எனையாண்டு காத்தருளும் இறைவா நன்றி. எங்கும் நிறைந்தோனே எல்லை இலாதானே, எங்கேயும் எப்போதும் என் குலம் காப்பவனே. நெஞ்சம் துணிய துணையாய் வருவாய், நேர்மறை உணர்வுகள் பெருகிடச் செய்வாய். உடலில் உறுதியை பெரிதாய் தருவாய், உனை உணரும் அறிவை என்னுள்ளருள்வாய். சுற்றமனைத்தும் காப்பவனே, செய்தொழிலில் ஏற்றம் தருபவனே, எடுத்த செயலில் வெற்றி கொடு, என் ஆற்றல் பெருகிட அருளை கொடு.
Now I wish to introduce our first invited speaker of the day, Dr. R.T. Agrawal, Associate Professor in School of Electrical and Data Engineering and the Director of Women Engineering and IT Program at the University of Technology, Sydney. She's completed her Master's in Physics and PhD on Modeling Methods for Optical Components from Indian Institute of Technology, Delhi. She was awarded Royal Society Postdoctoral Fellowship to study photonics crystal fibers at University of London. Her research interest lies on optics, modeling of photonics components such as solar cell, optical fibers, sensors, and laser, and etc. She is an expert in numerical methods for optics such as finite element method. She has published more than 80 research articles in reputed journals, written a book on FEM, and edited a book on trends in computational photonics. She is passionate about increasing the representation of women in science and tech engineering. She is currently Associate Vice President of Diversity for IEEE Photonics Society. Ma'am, over to you, ma'am. Now, please share your presentation.
Thank you. Thanks very much. So I just need to figure out how to share the presentation. Can you enable the sharing? I'm just trying to put the presentation. It's not, seems to be not showing. Yeah.
Ma'am, there will be a share icon at the bottom of your screen. You can share your
Yeah.
screen. You're a co-host now.
I got that. It's not showing the PowerPoint in that. So I'm trying to locate the PowerPoint in that. And for some
Okay.
reason, it's not showing the PowerPoint in my share option.
Try closing the PowerPoint and opening it again.
Okay, let's do that. Right. 1 second, just if I try to close the share, let me try again.
Yes, ma'am. I agree.
So now you're able to see my screen?
Yes,
Yes,
ma'am.
ma'am.
Thank you very much. And so I'd like to begin this talk by saying thank you very much to all of you for inviting me, and thank you for the wonderful introduction. Before I begin the talk, I'm going to do an Australian tradition, which is to acknowledge the traditional owners of the land on which I'm meeting you today. So UTS stands on the lands of the Gadigal people of the Eora Nation, and they are custodians of knowledge for these places. So I pay my respects to the elders past, present, and emerging. This is a tradition that's followed in Australia to honor the Aboriginal and Indigenous Australians who make up the original population of this country. And there are more than 200 different small nations who were part of Australia. So traditionally, before giving any public lecture or talk or event, the people will normally acknowledge the traditional owners of the land, which is what I have done. So in today's talk, I'm going to be talking about epitaxial graphene-coated silicon carbide nanowires for mid-infrared photonics. And in this talk, I'll start with a little bit of background and motivation for going down this route. So these days, nanophotonics is a very in area. Everyone is talking about nanophotonics. And why is that? That's because you have lots of applications for nanophotonics. So for example, whether it's nanophotonic circuits or making circuits smaller and smaller so that they fit into smaller spaces, and we can then try to go towards an all optical chip. Even in quantum computing, the need for nanophotonic circuits is very high. Then things like imaging, biomedical imaging and biological imaging, we want to be able to image smaller and smaller portions of the human body and at a more and more deeper scale. So we want to be able to look into the human tissue, deep into it, to see things like tumors and other things and see what's going on. Then there are applications in nano antennas, in free space optical communications, as well as in sensing. So in sensing, we want to be able to sense very trace quantities of a contaminant, a pollutant, or other things to be able to say that it is present, to what degree it's present, and what to do about it. So in terms of nanophotonics, why is this a challenging area? It's challenging because in traditional optics, we are limited by the diffraction limit about the spot size that we can form. So if you have a wavelength of light given by lambda and a spot size is formed using an objective, and that objective has a numerical aperture of say NA, and then the spot size has a diameter D given by this formula on the slide, which is roughly half the wavelength. So if we take the numerical aperture to be 1, just as a theoretical example, then the spot size is about half the wavelength. Now this is okay if your wavelength is small, but if your wavelength is very large, particularly in mid-infrared region where the wavelength is say 10 micron or so, then half the wavelength is also several micron. And a lot of applications that we are interested in when I was talking about sensing, etc., they are in the mid-infrared region, which is where the spectral signature of a lot of organic and chemical compounds exists. So if the spot size is so large, then the components required and the chips required will also be large. And that's one of the challenges. So we need to beat the diffraction limit. But with traditional optics, this is very, very difficult. So how do we overcome this traditional diffraction limit? Well, one way to do it is with surface plasmon polaritons or SPPs. I'm sure all of you have heard of plasmon polaritons. There are a lot of papers in this field these days. So just to give a basic reminder, what's happening here? Well, what's really happening in the formation of an SPP is a coupling of a photon with the oscillating charge carriers or electrons in the metal. So you have a metal dielectric interface effectively. And when the light is such that it is falling in the frequency region where the metal has a negative part of the permittivity, so the light is screened out of the metal and it cannot enter the metal. But what it does is it forms an SPP so that the charge carriers in the metal near the surface get coupled to the light, to the photon. And together they form this charged particle called the SPP. And as you can see from the left-hand side of this slide, you have a photon and you have these separate charge carriers which are not linked to each other. But once this oscillating charge carriers couple with the photon, the SPP shifts both the plasma photon as well as the surface, as well as the charge carrier, their oscillations as well. And this coupled creature behaves differently. So what we find is that this coupled SPP is able to screen out light and is able to confine light to below the wavelength of light. So earlier I talked about the diffraction limit, which was given by Abby, that was about half the wavelength. Now by doing this, we are able to go well below the wavelength. So one of the key advantages of SPPs is the tighter spatial field confinement. So what we call sub-diffraction confinement. Obviously, if you're able to confine the light into a very narrow region, you can also increase the field intensity in that small or narrow region. So it is possible to get high localized field intensity. And then with this very narrow region light being confined there, it was possible to manipulate photons at the nanoscale. And in this slide, I'm showing you some pictures that have been taken from journal covers or from journal articles, where people have either done theoretical or experimental work using nanophotonics. So for example, there's the NRL spacer, there's the plasmonic bow tie antenna, and then there's the plasmonic laser, which has been proposed, and people are trying to demonstrate these things, both theoretically as well as experimentally. So now I've already introduced to you this concept that we can have excellent sub-diffraction confinement with plasmonics. But conventional plasmonics, which is done with noble metals such as gold and silver, also have their own challenges. And there's a reason why conventional plasmonics has not yet thrown open the door for nanophotonics completely. And in this slide, that's what I'm going to discuss with you. So if you look at the right-hand side where I've got two graphs, on the top, you have a plot of the real part of the permittivity versus wavelength. And on the bottom, you have the same plot, but for graphene. So if you compare the right-hand side axis, y-axis of gold and graphene, you see that the imaginary part of the permittivity for gold is an order of magnitude or larger than that of graphene. So if graphene, the imaginary part of the permittivity, which is related to the loss, is about 20, in gold it is about 400 or 600. And because of that, the loss in gold is much higher. So these losses in the conventional plasmonics using noble metals lead to large optical loss. And that's because of the short lifetime of charge carrier oscillations. Large losses also are linked to the short average plasmon propagation length. So you basically have an SPP that's created which cannot last very long and is highly lossy, which is counterproductive to what we are trying to do. So we cannot use these SPPs very effectively in metal-based conventional plasmonics. The other problem because of loss, etc., is that the transmission throughput of these SPPs is small, and they are also harder to tune. So even though we can get sub-diffraction confinement, we can't tune it, cannot use it as effectively as we would like. So there are different approaches that we can use, and that's what I'm going to talk about next. So this particular slide shows you 3 or 4 different approaches towards use of plasmonics in nanophotonics, right? So there are 4 things here, and the third column, which is dielectric resonators, we will not discuss because this does not give subdiffraction confinement. The 3 other approaches are your traditional semiconductors. So if you dope the semiconductor extremely highly, then with this very high doping, it is possible for this to give you subdiffraction confinement. On the other hand, I've discussed what happens if we use graphene instead of metals. This gives you lower loss and gives you subdiffraction confinement. So this is an area which is developing quite a lot these days with graphene. But I'm going to now combine the second column graphene with this fourth column, which is surface phonon polaritons, and introduce a whole new area to you. So in the case of surface plasmon polariton, we were basically coupling the incoming photon with a charge carrier oscillations, free charge carrier oscillations in a metal. Now, instead of a metal, what we have is a polar dielectric. So a material in which the ions or the molecules are polarized, and they have phonons in them or oscillations of these molecules or ions inside the lattice of the material. And the light or the photon now couples to this lattice vibration or the phonon and forms what is called a surface phonon polariton. So inside the Reststrahlen band or over a narrow range of frequency, what we find is that the permittivity of the surface polar dielectric material goes from positive to negative. So it screens out the light. And because the light is screened out, it can couple to this ionic vibration, and this leads to subdiffraction confinement. So excuse me for jumping between the slides, and I'll go back here. So that's what gives us subdiffraction confinement. And we can then tune this surface phonon polariton over this range within the Reststrahlen band. Now, if I sum up some of the issues regarding graphene-based plasmonics and surface phonon polariton plasmonics, and then see where we are headed with this. So the potential challenges with graphene are that graphene photonics relies very heavily on the quality of the prepared flake of graphene. And depending on the substrate material, that affects the properties of the graphene as well. So if the substrate is not done properly, or if the flake is not well prepared, etc., this is going to impact the quality of the material. It's going to impact its properties. It's also very difficult to pattern graphene with substrates. And as I've said before, one of the challenges is that the lifespan of the SPP is not very long. So this is again an issue. On the other hand, with the polar dielectrics such as silicon carbide, we have certain other things which are useful. They have lower optical loss, and they have a longer optical phonon. So the lifetime here is a few hundred picoseconds, which is much, much better. And it is possible to pattern the polar dielectric. And therefore, by patterning it, it is possible to localize the phonon polariton resonance and then be able to play around with the manipulation of light and things like that. So this is a slide which shows you some pictures taken from journal articles, which are for photonic devices based on silicon carbide. So people have already demonstrated both theoretically as well as through experiments, things like micropillars in silicon carbide, and created a patterned surface of micropillars. And they've been able to show enhancement, emission, and other things with silicon carbide. People have also created things like microdiscs, as you can see in the middle column. And these beautiful microdiscs, such as these can be used for flexible photonic devices. And people have also created microcavities. So definitely the ease with which you can work with silicon carbide makes it easier to use this material and then to couple it with light to create this subdiffraction confinement. That's one of the aims. But there are, of course, limitations with every material, including with polar dielectrics such as silicon carbide. This negative part of, or rather the negative permittivity, only exists in the Reststrahlen band, which is a narrow region. So if we want to go beyond the Reststrahlen band, that's not possible with these polar dielectric materials. And how do we want to then operate? Because the ideal performance that we want is tunability broadband operation as well as low loss. So that would be the situation that we would have in the best possible world. So how do we deal with this? Well, what we are suggesting is to couple the advantages of two different material systems, take the advantages of graphene, which is tunability and broadband response, and couple it with the response that we can get from silicon carbide, which is long lifetime, lower loss, and long propagation length. And then together we can then form the plasmon in graphene and the phonon in silicon carbide to form what we call a surface plasmon phonon polariton. Now, in creating this new coupled beast, we need a resonant transfer of energy and momentum between the plasmon and the phonon. This requires adjustment of energy of the SPP mode, which is the plasmon mode, to match that of the SPHP, and also to match the momentum. So we have to match the phase of both the SPP and SPHP. If we can do that, then the resulting hybrid mode will display the properties of both the parent modes. So that is our aim in this research project. So one of the things that we are planning to do is to use coupling of SPP and SPHP by patterning. So by patterning, what we intend to do is to localize the modes and enhance Q factors, Purcell factors, etc. for nonlinear applications. And localizing, apart from localizing, what the patterning does is to also enable us to phase match the two different modes and to have a transfer of momentum between them. It also allows us to couple long-lived local resonances to low loss propagating modes. So here is just a schematic showing you surface plasmon polaritons and surface phonon polaritons. But since I've already explained this, I'll move on to the next slide. So now I've already given you a sense of where we are going with this. We want graphene and we want the polar dielectric like silicon carbide. So epitaxial graphene is the material or the form of graphene that we are using. And we've used nanowires to do this. So in plasmonics, there are different figures of merit that are used to define whether a material system or structure is performing well or not. The first figure of merit is to do with propagation, which you see on the left top here. So this is showing you this particular, this figure of merit, which is the plasmon propagation length divided by the polariton wavelength. This tells you how much it will propagate before it dies out. And as you can see in this graph, the blue curve is for the silicon carbide, the red is for graphene, and then the orange and the purple are for graphene divided by silicon carbide for different Fermi energy of graphene. This is perhaps not so interesting because you can see within the Reststrahlen band how the materials behave. But if you look at the second figure of merit, which is the confinement, that's the wavelength divided by the penetration depth into the material. And here is where things get really interesting. And you can see from here that the confinement figure of merit improves tremendously if you have graphene on silicon carbide. So the purple curve here, you can see that you get really good confinement in the Reststrahlen band compared to say plain graphene or plain silicon carbide. So by combining these two materials, we can really confine the wavelength of light or the spot size, etc., that we would be able to get. So I'm going to talk a little bit more about this. Now, this is showing you a schematic of how we are creating this kind of a structure. So this is using a catalytic alloy mediated approach. And the end result is to get a thin sheet of graphene, about a bilayer or a single layer on top of 3C silicon carbide, which is sitting on a silicon substrate. This is for a planar surface, but we can, of course, do things for non-planar surfaces as well. Before I go to the non-planar surface, I just want to share some results here with you. So if we look at the experimental results of FTIR, and we look at the reflectance from the structure, we see that the plain silicon carbide, which is represented in blue, has this particular dip around 950 centimeter inverse, and a peak in reflectance around 800 centimeter inverse. Coating it with graphene gives us the black curve. And there isn't a shift in these features. They stay roughly the same. So we can't really notice the impact of graphene in the structure. And we also did this through simulation, where we did this in using FEM in COMSOL software. And what we find is that the silicon carbide and the silicon carbide coated with graphene, the features do not change much. So in the planar structure, there doesn't seem to be that much advantage. Now, from moving from a planar structure where our silicon carbide was slightly thick, we have reduced the thickness of the silicon carbide on the left-hand side to 50 nanometers. So when the silicon carbide thickness is extremely small, we find that the behavior of the features changes a little bit. And instead of having very prominent dips at about 950 centimeter inverse, the dips become smaller and the peaks at about 800 shift a little bit. But again, the behavior is not substantially different, although the thickness is of course making a difference. So what we recognize is that the thickness of silicon carbide is important. But now instead of being in a planar configuration, we have moved to creating a nanowire of silicon carbide and then coated it with graphene. And if you compare these two graphs from left to right, you can see that the behavior, the features have changed substantially. So clearly something special is going on with the nanowire. And this is what we will be exploring. But comparing the two nanowires, plain silicon carbide and the one coated with graphene, we find again their features are similar. They're not too different between each other. Now, what we realized is that experimentally using the alloy-mediated catalytic process on the silicon carbide nanowires results in a bunch of nanowires that look like a forest, which you can see on the right-hand side of this slide. So you can see this very intricate and random structure of coiled nanowires which are lying on each other. So this is quite different from having a nice, smooth, periodic arrangement. And if you look at the reflectance of this structure, so the bare silicon carbide nanowires give you the blue reflectance curve. But as soon as you look at this random nanowire structure, you get the red reflectance curve. So you have a prominent dip at about 1050 centimeter inverse and a dip at about 793 or close to 800 centimeter inverse. And the reflectance is high in between, which is inside the Reststrahlen band. So obviously, as soon as you graphitize the nanowire, its behavior changes substantially from blue to red. And that's where the interesting features lie. Now, what we realize is that when we are graphitizing the nanowire, there is also a very thin layer of oxide that gets formed. And that is what is shown here on the left diagram. So you have the blue silicon carbide region with a very thin gray oxide layer. And then at the outer side of the oxide layer is the single monolayer or bilayer of graphene. And when we simulate this particular structure, so your silicon carbide at the center, then an orange oxide layer, and then this blue, thin blue layer, which shows the graphene. And we do the simulation for this. We find that the red curve that we get is quite close to what was obtained experimentally. So once again, to recap, bare silicon carbide nanowire is the blue curve. If you graphitize it, the behavior between the blue and black curves is not very different. You need to include the impact of the oxide layer to be able to sufficiently capture the behavior of this graphitized nanowire. And then this looks quite similar to that of the actual experimental results. So this is just showing you the comparison. As you can see that they look quite similar, the experimental and the simulation results. Well, so what have we done? What have we achieved by doing this? What we have achieved by doing this, if you concentrate on the right-hand side of this figure in the right-handmost column, here I'm plotting the field inside the oxide layer. And you can see from the field in the oxide layer that the field drops very sharply outside the oxide layer. And this oxide layer is about 4 to 10 nanometers thick. So about 4 to 10 nanometers thick. And inside that 10 nanometer or 4 nanometer layer, most of the field is concentrated. And as soon as you go outside that, the field drops drastically. Now we are in this mid-infrared region. So the actual wavelength of light is much higher than nanometer region. So what we are getting is substantial subdiffraction confinement here. That's why this particular graph is really important, because we are really going below the diffraction limit here. So this is just showing you what happens to the reflectance of the structure for different oxide layer thickness. If you don't have any oxide, you just have the bare silicon carbide, you get a certain reflectance. You introduce the graphene but no oxide, you get the red curve. And then as you introduce the intermediate oxide layer, you start getting this feature here in the Restronland band. And this is being formed because of the coupling between the plasmon. So there's a plasmon formed between the graphene and air. And there is a phonon polariton which couples with the plasmon, which is at the oxide silicon carbide thing. So if this oxide layer is too thick, the phonon and the plasmon will not couple. That's why if the oxide layer is very thick, this feature in the middle disappears. So the oxide layer has to be thin enough for the coupling between the phonon and the plasmon. And this is also showing you what happens when you have subdiffraction confinement, how you get extremely large field enhancement. Sorry, what was that? I cannot hear you. All right, maybe my time is up, so I'll hurry up and try to finish.
No, ma'am. You can take your time. I think there was an error. Somebody unmuted by mistake.
No problem. All right, so for the feature which is formed in this particular area, this first feature, which is because of the coupling between the phonon and the plasmon, we find for that particular mode, if we take a ratio of the electric field inside the oxide layer divided by the electric field at this interface, we find that the field is enhanced by a factor of almost 75 at the very maximum for an oxide thickness of 2 nanometers. And this is about, say about 60 or so for an oxide thickness of 3 nanometers. And as the oxide thickness increases, the coupling decreases and hence the field enhancement decreases. But a 60, 70 times field enhancement shows you how powerful subdiffraction confinement is for enhancing the field as well. We also talked about the tunability of this system. So there are different ways we can tune it. We can tune it by changing the Fermi level in the graphene by applying a potential or a voltage. We can also tune it by changing the doping, etc. So in conclusion, I'd like to say that using simulations and experiments, we have realized enhancement of mid-infrared reflectance for graphene-coated silicon carbide nanowires. And the intermediate oxide layer between graphene and silicon carbide plays a key role in this system. And an optimal thickness is needed for subdiffraction confinement and strong field enhancement. And this is likely because of the coupling between the surface plasmon polariton and the surface phonon polariton. We can also predict that we can tune the system by tuning the Fermi energy in graphene. So with that, I'd like to stop and say thank you very much for your time and for your attention.
Thank you, ma'am. Thank you for your presentation. Thank you, ma'am.
Thank you.
Now the session open for the questions.
Madam, this is Justin from NIT. Thank you for the nice presentation. Can you hear me?
Yes, Dr. Justin, I can hear you. Please go on.
Okay. So thanks for the nice presentation. And I just wanted to know what is the mechanism behind the coupling of the the surface layer according to the thickness. What is the mechanism?
Okay, so what we think about the mechanism is typically in any structure, the fields, if the tail of the field of the plasmon, which is here, and the tail of the field of the phonon, if these two tails are able to reach each other, then they can couple. That's what we expect. But we need to do some more experiments with S-norms to be able to actually look at the fields experimentally and to verify this. But remember, these nanowires are very thin. They're really, really small, and they're quite complicated. So being able to look at the field inside a 2 nanometer region is not easy. That is one of the things that is currently being done.
Thank you, thank you. And one more question maybe like, how could you ensure that the surface graphene, how do you characterize the surface graphene layer?
Well, that's one of the key things to do with graphene, is to make sure that the surface is smooth and it is uniform, etc., etc. So one of my collaborators, Professor Francesca Jacopi, is an expert in graphene and in experimentally fabricating graphene. So the process that I mentioned in one of the slides, the catalytic approach, is something that she has invented. And I think my area is more simulation rather than fabrication. So unfortunately, I can't give a lot of detail on how smoothness of the surface is ensured. But I think if you look at the paper that is referred in the slides, you can look at the process and see it in more detail.
Thank you, madam. Thank you once again.
Hello, ma'am.
Yeah.
I have a question.
Sure.
With comparing simulation from fabrication, what would be the discrepancy between the simulations and the actual case?
Are you asking what is the cause of the difference, or are you asking how much is the difference?
Both, actually both.
Okay. So the amount of difference can vary from situation to situation. In our case, the location of the features is quite similar, but what is the intensity is not of the actual reflectance. That is not exactly the same. And with experiments, we have to do, so where the nanowires are deposited on the sample, you have to do several measurements across different locations on the sample and then average across them. So at each location for different nanowire, you'll get slightly different experimental results. So actually the error bar in the experimental results is also present, right? And then you compare the two. So what I'm showing you is some of the more preliminary results. Now, coming to the reason why there will be a little bit of discrepancy between simulation and experiments is, in the simulation, we are assuming a very perfect circular nanowire, and we are simulating a single nanowire applying periodic boundary conditions. So it's almost acting like a periodic structure which is repeating. But if you look at the SEM image that I showed you in the slide, the real structure is a very convoluted random forest. So it's not going to be, the simulation is going to be a perfect replica of the actual experimental thing. So this is a first model, and then we would introduce more complexity to model that kind of randomness. The other thing is that the nanowire is not going to be smooth. So we have to introduce more roughness in our simulations. We also have to think, is the coating of oxide perfectly uniform, or is that also changing? Those are some of the features that have to be varied. So I hope that kind of gives you some insight into the interplay between simulation and experiments.
Yes, ma'am. Thank you. When it comes to percentage, what is the error bar? How much can we expect?
I don't think there is a fixed thing to say this is how much it should be or cannot be. It depends on the context of the experiment itself. Okay. So in some cases, you will have a certain measurement error in your instrument, right? So what is the measurement error in your instrument, etc.? And then how much is the tolerable I should say how much accuracy you want. So within that, you have to see how to compare the two. Even simulation will have a certain amount of error associated with it, 3%, 4%, something. So then you have to see, compare the two and say how much is it. And it would differ from experiment to experiment.
Okay, thank you very much.
There is another question in chat box. Can we use nanophotonics in the field of data transfer with a short range like computer circuits in similar way we use optical fibers for the internet connectivity?
Well, that is something definitely people are interested in, and particularly for quantum computing and for optical computers, that's something that they're interested in. I can't tell you more detail than that, but for sure there is an interest in that. Because with nanophotonics, you would have this very small circuits, very short circuits, and you would confine the light so high or so well that you would be able to transfer it. The problem is always the loss. So can we minimize the loss sufficiently for this to work? That is the current challenge.
Is there any other questions from audience? If there is any question, I thank you very much, ma'am, for your valuable time with me. Thank you, ma'am.
Thank you. Thank you.
Dear participants, the second second section will be continued at 11 o'clock. Thank you.